We learned that the emission of long-wave radiation depends on the temperature of an ecosystem. How hot ecosystems get depends in part on how much short-wave radiation is absorbed, but also the partitioning of absorbed radiation. The authors state that net radiation, the radiative energy absorbed by an ecosystem, is approximately balanced by energy that is transferred out of the ecosystem by non-radiative processes. Surface temperature is important for long-wave radiation flux. When we look at an ecosystem, energy gets partitioned among a few different processes. One of those is ground heat flux. And essentially, ground heat flux is the amount of energy that's absorbed, at least temporarily, by the ground. And then there's also latent heat flux. And latent heat flux is essentially the product of L and E, where L is the latent heat of vaporization, which is the amount of energy it takes to turn liquid water into vapor water, and then the evapotranspiration rate. So the amount of energy that goes into evaporating water is called latent heat flux. And again, the latent heat flux is a product of the amount of energy that's required to vaporize a given unit of water and the amount of water that is turned into vapor. Now, thirdly, in addition to there being ground heat flux and latent heat flux, there's also sensible heat flux. And again, sensible heat flux is the amount of energy that goes in to warming the air immediate to a surface. Another component is also the storage of chemical energy. And photosynthesis is one way, for example, that energy that's in shortwave radiation gets stored in chemical forms. Now, that component of an ecosystem radiation budget tends to be relatively low, somewhere in the order of 5%, or 5% of the amount of energy that's absorbed goes into chemical energy. If we take a look at the equation for net radiation for the different components that we just covered, again, we start with net radiation, and net radiation here is going to be positive when it's directed towards the surface. So essentially, when an ecosystem absorbs radiation on the whole, we have a positive net radiation. And then we have our four components, where H is sensible heat flux, we have latent heat flux, ground heat flux, and storage, or changes in storage. And so the radiation budget can be decomposed into four components here, and it's the amount of energy that goes into warming the air, that goes into evaporating water, that goes into warming the ecosystem or the ground itself, and then how much gets turned into chemical energy. The main two components of any ecosystem's radiation budget tend to be these two components. Ground heat flux tends to be relatively low, and we talked about how storage is low. And so understanding the partitioning of absorbed radiation really is associated with determining the balance between sensible heat flux and latent heat flux. What this figure is, figure 4.3, runs through differences in ecosystems in the partitioning of energy between latent heat flux and sensible heat flux. So on the x-axis, we have latent heat flux, which is the amount of energy that goes into evaporating water. The units on this are megajoules per meter squared per day. And on the y-axis, we have sensible heat flux, which is the amount of energy that goes into warming the air. That again, units megajoules per meter squared per day. So the same units. 3, 6, 9, 12, 15, 3, 6, 9, 12, 15 shows that you have the same scales here too. This dotted line is the one-to-one line. And essentially, if you fall on this line, you have equivalent amounts of sensible and latent heat flux. Now, in this graph, what we show is that there are different ecosystems for which we've determined latent and sensible heat flux: deciduous forest, conifer forest, Mediterranean ecosystem like the chaparral that we would have talked about, agricultural systems, tundra, and grasslands. And then they calculate ratios that fall along these lines. right here we had this beta equal to 1, and that means you have equal sensible to latent heat flux, 3 and 3, 6 and 6, 9 and 9. And this beta is known as your Bowen ratio. So we'll talk about a Bowen ratio, which determines, if you know the Bowen ratio, you know the partitioning between sensible and latent heat flux. Ecosystems that are up here, where your Bowen ratio is higher than 1, what that means is that for a given amount of sensible heat flux, the partitioning is for there to be a lot less latent heat flux. When your Bowen ratios are less than 1, you have a lot more latent heat flux than you do sensible heat flux. So these evaporate a lot of water relative to the amount of heating of air there is, whereas these heat the air a lot more than they evaporate water. Let's take a look at what some of these systems are. Systems that tend to have a lot of leaf area and be relatively moist, like deciduous forest or agricultural systems, you can see are down here. Here are the agricultural systems, here are deciduous forests, and these have a relatively low Bowen ratio. These ecosystems evaporate a lot more water than they do heat the surrounding air. In contrast, boreal forests or conifer forests, such as these over here, are ones where you don't have a lot of transpiration and you have a lot of heating of air. And so in this case, these systems will warm the air a lot more than they'll pump water into the atmosphere. And then these Mediterranean climates, for example, you get this wide range where there are some ecosystems that transpire a lot more water than they do heat the air, and you have some with a relatively high Bowen ratio, which is the converse of it. Now, that covers the basic patterns of sensible heat flux and latent heat flux. Ground heat flux is something different. And essentially, ground heat flux is more or less neutral at a daily scale. What that means is that the amount of energy that's absorbed by an ecosystem and goes into heating the ground, essentially, is during the day is balanced out by how much is lost at night. Now, ground heat flux does vary across the Earth and across ecosystems, and in general, you have a greater magnitude of ground heat flux in colder places. So a lot of energy in the Arctic, for example, during the summer goes into heating the ground. So this is frozen ground at the beginning of the summer. It's very cold, and a lot of energy goes into heating that up. In the fall, you're going to get the opposite pattern with a lot of loss of energy from these systems as they release heat into the atmosphere. And somewhere on the order of 10 to 20% of the energy that is absorbed in the Arctic, for example, goes into ground heat flux. In addition, lakes tend to have high ground heat flux. And that doesn't mean that it enters the sediments, but it just means that it's absorbed by the ecosystem itself. And the reason for that is that energy that goes into a lake doesn't necessarily evaporate a lot of water, even though it's a wet ecosystem. And it takes a long time for these to heat up because you have a really high density of well-mixed mass too. And so your sensible heat flux is relatively low because these waters tend not to be that much warmer than the air quite often. But it takes a lot of energy to heat up the water that you find in a lake, and therefore you can have really high ground heat flux in a lake. And in these systems, for lakes, ground heat flux can be somewhere on the order of 50% of the absorbed radiation budget. So again, when we want to think about the energy budgets of ecosystems, really the important things to think about are sensible and latent heat flux. There are examples where we need to think about ground heat flux and being an important component of it. I don't want to discount that. But really, when we start to talk about radiation budgets and partitioning of absorbed radiation, you start to think about sensible heat flux and latent heat flux and the ratio between the two, that Bowen ratio.